Hello, welcome to lecture 10 of this course. This is the final lecture in module 1. In the last lecture, we have learned about coherent states of harmonic oscillator. In this lecture, we are going to learn and discuss about the another important quantum states of harmonic oscillator called squeeze states. These states has very important applications, particularly in precision measurements, and in particular one can obtain precision better than the one set by the so-called Heisenberg uncertainty relation. Finally, we are going to summarize what we have learned in the module 1 of this course. Let us begin our discussion on squeeze states. It is an important class of quantum states of harmonic oscillator or quantized electromagnetic radiation. As we learned in the last class about coherent state, by considering a ground state and then displacing it, so we have taken a ground state, and if we displace it, then we get the coherent state. Similarly, we can understand squeeze state by taking the ground state of a harmonic oscillator and then squeezing the ground state, and then we are going to get the so-called squeeze state. So squeeze state is going to be represented by this k xi. Let me explain it a little bit more clearly. Say, let us take the usual ground state of a harmonic oscillator with, say, frequency omega. Let us say you know that the ground state of a harmonic oscillator is Gaussian, so it is what we have. Suppose this is what we have, and this harmonic oscillator has the natural frequency to be, say, omega. Now increase the curvature of the harmonic oscillator. If we increase the curvature of the harmonic oscillator potential, that implies squeezing of the harmonic oscillator. So this is what we are going to get. Because of that, you see the ground state is getting squeezed, and the frequency of the new harmonic oscillator is now we increase the curvature, and then as a result of this, ground state is getting squeezed, and its frequency, say, omega tilde, is the new frequency of the harmonic oscillator when after increasing the curvature, and omega tilde is greater than omega. Let us now do one thing. Let us express the annihilation operator of the, let me just write here, let us express the annihilation operator of the new harmonic oscillator in terms of annihilation and creation operator of the old harmonic oscillator. Okay, let me write here, for example, what I mean by old harmonic oscillator. Say, in old harmonic oscillator, the frequency of the harmonic oscillator was omega, and new harmonic oscillator, the frequency is omega tilde. So the position operator would be represented by x cap. You know that would be, say, q0 plus a dagger. A is the annihilation operator, a dagger is the creation operator, and q0 is equal to h cross divided by twice m omega under root. That is for the old. Then I will also talk about the new a little bit later. Okay, and then the corresponding momentum operator would be I m omega q0 a dagger minus a. All right, and therefore you can immediately write a annihilation operator as 1 by twice q0 x plus ip by m omega. All right, so this is what I have, and Now the new harmonic oscillator, let us, its position operator is x cap, say 0 point fluctuation is q0 tilde, and now annihilation operator, let me write it as b, and then creation operator is b Dagger for the new harmonic oscillator. And you see that q0 tilde is now its, say, frequency. It is the same harmonic oscillator, only we have just change the frequency or increase the frequency, so it would be the only the frequency is now getting changed. And momentum operator would be I m omega tilde q0 tilde b Dagger minus b. Okay, and therefore b, this operator I can write it as 1 by twice q0 tilde. You have here x plus ip by m omega tilde. All right, so now the next thing is to express this annihilation operator b in terms of a and a Dagger. That is, you can trivially do that. So you have 1 by twice q0 tilde. So in x, let me write it this one. Okay, so x would be q0, so I'm just using this one, a plus a Dagger, and I, you have here I 1 by m omega tilde, and p operator you can write it as I m omega q0 a Dagger minus a. Okay, so this is what you can do, and if you actually do the calculations, it's very trivial. So you should be, finally, I encourage you to do it. You should be able to show that this would turn out to be 1/2 square root of omega tilde by omega, and you will have a 1 plus omega by omega tilde plus a Dagger 1 minus omega by omega tilde. Alright, so this is what you will have. Now clearly the new annihilation operator is a combination of all annihilation and creation operator. So if I now write, say, cos hyperbolic r is equal to half square root of omega tilde by omega plus omega by omega tilde, and sine hyperbolic r I can write it as 1/2 omega tilde by omega minus omega by omega tilde under root. So you will immediately see that if I write it like this, cos hyperbolic r minus sine hyperbolic square r is equal to 1. You can verify it very easily. Then in terms of this cos hyperbolic r and sine hyperbolic r, I can express my new annihilation operator b as cos hyperbolic r a plus sine hyperbolic r a Dagger. Okay, so this is, you see, the annihilation operator of the new harmonic oscillator after we squeezed it is how it is related to the annihilation and creation operator of the old harmonic oscillator. And this transformation is actually known as Bogoliubov transformation. So I am going to build up everything around it, so that's why I have introduced it this way, and you will see the meaning. And another thing, let me just comment here, that because cos hyperbolic square minus sine hyperbolic square r is equal to 1, and since omega tilde is greater than omega, so this implies that this parameter r is greater than 0. Now let us look at the variance of the new harmonic oscillator. So variance of position or x operator of the new harmonic oscillator, I can write it as h cross divided by twice m omega tilde, where psi tilde is the wave function of the new harmonic oscillator. And because we are considering the ground state of the harmonic oscillator, so the variance is nothing but the square of the 0 point fluctuation, which is simply h cross by twice m omega tilde. This I can further write as h cross by twice m omega and omega by omega tilde, and you can easily recognize that this is again nothing but the variance of the position operator for the whole harmonic oscillator. So and it would be multiplied by omega tilde. Now as you can see that omega tilde, that is the harmonic frequency of the new harmonic oscillator, which is greater than the old harmonic oscillator frequency. So clearly we can see that the variance of x for the new harmonic oscillator is less than the variance of x for the old harmonic oscillator. Okay, and it is a clear indication that the uncertainty in position is decreasing. On the other hand, if you look at the variance of the momentum operator for the old new harmonic oscillator, that you can simply write it as h cross m omega tilde by 2, because we are in the ground state, who is further I can express it as omega tilde by omega h cross m omega by 2, and this guy is nothing but the variance of momentum of the whole harmonic oscillator. So this is I can write it as a variance of this position operator in the whole harmonic for the whole harmonic oscillator. So here again you can see that the uncertainty in momentum is now getting increased. So what you actually see that the so-called position is uncertainty's position is decreasing at the cost of increase in the uncertainty in the momentum. However, you should note that the variance, the product of the variance of the position and the variance of the momentum, that would be constant, and that would be h cross by 2 whole square. Okay, and this is basically same with the original unsqueezed harmonic oscillator, and that means that the uncertainty product, that is delta x into delta p, is equal to h cross by 2, and this is still preserved. And actually because of that reason, both coherent states and the squeeze states are called Gaussian states, because for Gaussian states only the uncertainty product, that is uncertainty in position and uncertainty in momentum, that product is minimum, that is h cross by 2. Now what about the squeezing operator? So let us now discuss that. What about the squeezing operator, that is as xi? But before I go into discussion of squeezing operator, first let us guess the squeezing Hamiltonian. Now you see that we got the squeezing annihilation operator from our preliminary analysis like this: cos hyperbolic r a plus sine hyperbolic r a dagger. Now you can actually prove that if you take a dagger for the squeezing annihilation operator, this is an a as q. If this is the number operator for the squeeze state, this does not conserve the particle number. It does not conserve the particle number, unlike a and a dagger, a, which is the number operator originally. This conserve the particle number, and that's the reason we write down the Hamiltonian for the normal harmonic oscillator as h cross omega a dagger a plus half. Okay, for harmonic oscillator. But now the thing is that what about the Hamiltonian for the this is squeezing? Okay, for the squeeze states of the harmonic oscillator. So let us guess. Let us say our squeezing Hamiltonian for the squeeze state is of this type, so it should be quadratic in the this annihilation and creation operator. Let us say it is A dagger, say I, let me first write and I'll explain. I s cross h z star a square minus z a dagger square, because it has to be Hermitian, where z is a general parameter. Z is a general parameter. All right, and so this is what I have. So h cross omega has the dimension of energy, and so this is our assumption about the Hamiltonian for the squeeze state harmonic oscillator. So if whether it is correct or wrong, we will get to know if we look at the time evolution of the annihilation operator, because the time evolution of this annihilation operator, if it's coincide with what we have got as the annihilation operator for the squeeze state, then we will get to know that all right, that our Hamiltonian is correct, because you remember that this one we worked out as annihilation operator, we denoted it by B so earlier. Now from Heisenberg representation, which we discussed in an earlier class, we can write this time evolution of this annihilation operator as e to the power I by s cross. Now our squeeze Hamiltonian is this, and then this would be a e to the power minus I by s cross h s cube t. Alright, so this is what I have. Now to work out the time evolution, let us begin by writing down the Hamilton's equation of motion. So I have a dagger of t, that would be Heisenberg equation of motion will give me 1 by I s cross a Hamiltonian, okay, h cube. So if you already I guessed what is my, if I just use this equation, then you can immediately work out this as let me just write it down, you please verify. You should be able to get it minus omega z a dagger square. This is what you will get, and this can further you can simplify, and then you will get the a dagger dot time derivative of a would be equal to minus twice omega z a dagger, and the for the creation operator it would be a dagger dot, okay, that would be equal to minus twice omega z star a. So let us say this is my equation number 1 and this is my equation number 2. Okay, now from these two equations I can get a uncoupled equation. If I take the time derivative of equation 1, then I can write it as a dagger double dot, a double dot annihilation operator. I'm taking the time derivative, so I will have twice omega z, and then this would be minus twice omega z star a, which you can easily see. So therefore what I will get here would be I will get it as 4 omega square mod z square a. So therefore I get a equations for the annihilation operator, and I can write it as say lambda square a, where lambda square is equal to 4 omega square mod z square. Okay, so let us say this is my equation number 3. So this equation could be easily solved, and we know the general solution of this type. Say a of t is equal to some constant, say c1 cos hyperbolic lambda t plus c2 sine hyperbolic lambda t. All right, and let us say this is my equation number 4. Now we know that at t is equal to 0, we have a at t is equal to 0 is simply, let us write it as a of 0. And if I put these initial conditions in equation 4, immediately you see that C1 is a of 0. Okay, on the other hand, if you take, alright, so let me just work it out. If you take the time derivative of this equation 4, then you will get it as C1 lambda sine hyperbolic lambda t plus C2 lambda cos hyperbolic lambda t. And then because of the fact that lambda square is equal to 4 omega square mod z square. Okay, so let us take lambda is equal to minus twice omega or into mod z, and this minus sign is taken rather than the plus sign so that we can reproduce equation number 1. Okay, that's the reason I have taken it like this. And therefore now at t is equal to 0, I have a dot at t is equal to 0 would be simply from this equation, you see, that would be C2 of lambda. And then I can easily work out from equation 1. Okay, let us go to equation 1 here. You will see I have a dot, that is from here I can get, these are very simple analysis, I am doing it in details, but I could have left it for you, but okay, let me do it twice. You have omega z a dagger t is equal to 0 is equal to C2 lambda. And from here what I can do, I can write it further twice omega say mod z, this is z, so mod z say e to the power I theta a dagger t is equal to 0, and you have C2 and lambda I have taken it to be like this, so I have twice omega mod z. So from here I can find out my other constant, that is C2 is equal to a dagger at t is equal to 0 e to the power I theta. So therefore what I get finally is that I get a of t is equal to a of 0 cos hyperbolic lambda t, okay, and plus a dagger 0 e to the power I theta sine hyperbolic lambda t. Or I can write it as a of t is equal to a of 0 cos hyperbolic r plus e to the power I theta a dagger 0 sine hyperbolic r. Okay, where I have taken lambda t is equal to r. So this is what I got. And in fact if you look at our earlier treatment, which was very elementary treatment we have taken, we got it exactly the same equation, apart from here what the new thing we got is that now we got e to the power I theta, which is actually in our earlier treatment that was not the case. Okay, so okay, let me write it again. This is not what we got from our earlier treatment, because our squeezing was only along the x direction, but here I am now talking about a general squeezing can be done in general. Anyway, I will come to that. So you see, that means that the Hamiltonian that we have considered for squeezing is perfect. So our guess is correct. So the squeezing Hamiltonian, we can write it as I s cross omega z star a square. That was our guess, and by this guess we got the correct expression. So I can now write it as I s cross omega mod z e to the power minus I theta a square minus e to the power I theta a Dagger square, or I can finally write it as the squeezing Hamiltonian is I s cross omega mod z e to the power minus I theta a square minus e to the power I theta a Dagger square. Okay, let me box it. So this is what I got. Okay, now what about the squeezing operator? So squeezing operator would be simply e to the power minus I by h cross h sq t. Alright, so this actually you can verify, but let me just simplify it. It is exponential omega mod z t e to the power minus I theta a square minus e to the power I theta a Dagger square. Okay, so this is my squeezing operator, and because we have already taken that r is equal to lambda t, which is minus twice omega mod z, that is what our lambda. So therefore I can finally write this expression I by h cross h sq t is equal to exponential r by 2 e to the power minus I theta a square minus e to the power plus I theta a Dagger square, or this is basically my squeezing operator. And therefore if I now define a quantity, say xi is equal to r e to the power I theta, then we can write as xi is equal to e to the power minus I by h cross. This I am writing again and again, just you should remember it, and then I can write it in the very familiar form, exponential half xi, okay, xi a Dagger square minus half xi star a square. Okay, this is what we have. Or finally, let me just write down the squeezing operator separately like this: exponential half xi a Dagger square minus half xi star a square. So this is a very important result, and it's a important operator, and this is we are going to exploit in this course. This squeezing operator is unitary. Squeezing operator is unitary, and the squeeze state xi can be created from vacuum just by applying this squeezing operator on the vacuum state. Also, you can see that the squeeze state is normalized because of the fact that Si is unitary. So because of this you can immediately see, because vacuum state is, this is anyway identity operator, so vacuum state is normalized, so the this squeeze state is also normalized. Let me reiterate once again that when we originally obtained the expression for the annihilation operator earlier, let me go to that expression once again, where we got it from our elementary treatment. Here you see, here we did not had this term e to the power I theta there, and because originally we assumed that the direction of squeezing to be along a particular direction, and in this case it was along the x direction, but the new expression which we are having e to the power I theta, this factor is also there, so that is more general, and actually now we can talk about squeezing along any direction. So this is much more general expression we have, and generally in literature this is the expression that we are you are going to get. Finally, let me quickly list some of the useful relation that you can immediately derive, just the way we have done it for the displacement operator in the context of coherent state. For squeeze state also, squeezing operator case, you can have as these properties. So S Dagger xi is equal to S minus S inverse xi, and that is equal to, you can show that that would be nothing but, because of the structure of the operator, this relation you can immediately prove. And I leave it as a exercise to you. You can show that S Dagger xi a S xi, you should be able to get a cos hyperbolic r plus a Dagger e to the power minus I theta sine hyperbolic r, and you will, for the annihilation or for the creation operator, you will get this kind of expression. So that would be a Dagger cos hyperbolic r plus a e to the power, I think this is plus I theta, e to the, here it will be e to the power minus I theta sine hyperbolic r. These are very useful relations, and I encourage you to work it out. Okay, there is a small correction. This should be a Dagger. Okay, now finally let me give a quick graphical representation of squeeze state in free space. Here let me make one point clear, that the squeeze state I am considering here is the so-called squeezed vacuum, because I have obtained it by squeezing the ground state or the vacuum state. So this is called squeezed vacuum state. Okay, to represent it graphically, let me define two quadrature operators, say x cap as, say, a plus a Dagger, and y cap as I into a Dagger minus a. As you can see from the construction, that x cap is analogous to the position operator and y cap analogous to the momentum operator. Now if we calculate the variance of this position operator in the squeeze state, the variance is defined as expectation value of x square minus expectation value of x whole square. If we calculate it in the squeeze state, and maybe we'll do it in our problem solving session, or you can try it yourself, you will get it as e to the power 2r in the squeeze state we are calculating. Or in this on the other hand, the variance of this momentum operator or y quadrature would turn out to be e to the power minus twice r. So you see this the variance in y is decreasing, while the variance is x is getting increased. So this we can represent it graphically in this phase space by, this is my x-axis and this is my y-axis. Initially I had my vacuum state like this. Now after squeezing, what is happening, that the quadrature in x is getting increased. So this is what I get here, and y is decreasing. So you see the y quadrature is getting squeezed and the x quadrature is getting amplified. So this is what we mean by squeezed vacuum state. This is what we mean by squeezed vacuum state. Similar analysis you can do for coherent state. For coherent state, you will see that the quadratures actually does not change, but what happens is that, as you know, that the coherent state is basically displaced vacuum, so quadratures remain maintained, but this vacuum state is getting displaced in this phase plot. So this is what is our coherent state. All right, another point let me make, that apart from this squeezed vacuum state, we can have also squeezed coherent states. We can have squeezed coherent states as well, and this can be obtained first by creating a coherent state, and then you squeeze the whole thing, then you will able to get the so-called squeezed coherent states. So with this we have completed the first module of this course. Now let us have a quick recap of what we have learned in the first module of this course. In lecture 1, I have given a general introduction to the course followed by motivation behind the course. Then in lecture 2 and 3, we learned about two-level systems or two-level atoms. There we saw how one can write the Hamiltonian in a very compact form in terms of the Pauli matrices, and we also learned about the so-called Heisenberg representation or Heisenberg picture. And in this picture we learned that the operator, any operator, quantum mechanical operator, say A, is become time dependent, and the wave function is time independent. On the other hand, in the so-called Schrodinger picture, which we are generally used to, there the time dependency is associated with the wave function, and the operator there is time independent. And in an analogous way to the Schrodinger equation, which gives the time evolution of the wave function, in the Heisenberg picture the operator evolves with time as per the so-called Heisenberg equation of motion. Here I have written down the Heisenberg equation of motion, provided the operator A is not exclusively dependent on time. Then we saw, you applying this Heisenberg equation of motion, that the time evolution of the Pauli operator, and we also saw that the expectation value of the Pauli operator, it basically precesses around an arbitrary vector, say epsilon, and it precesses with some frequency, say 2 twice E by h cross. That is the precession frequency with which the Pauli expectation value of the Pauli vector rotates, and this expectation value of Pauli vector or is has a name, and it is also called the so-called block vector. Alright, then after that we worked out the eigenvalues and eigenvectors of this Hamiltonian, and also we discussed about the so-called avoided crossing, and we saw that in the when there is a term, a non-zero term in the off diagonal of the Hamiltonian, then it basically because of that this energy level no longer cross, and that is what is called the avoided crossing. After that we discussed the two-level system under the time dependent driving, and there also we learned that under the so-called rotating wave approximation, the Hamiltonian can be again written in a compact form using the Pauli matrices. And then we went on to discuss the so-called Rabi oscillations. In lecture 4, we studied about a two-level atom interacting with a classical field. The classical electric field was taken at the position of the atom, because we considered that the atom is size of the atom is much smaller than the wavelength of the electric field, electromagnetic radiation, and the ground state of the atom was considered to have an energy 0, and the excited state has energy E is equal to h cross omega 0. Omega 0 is the resonance frequency, and in this case the atom is considered as a quantized entity, and the electric field is considered as a classical entity, and that's why this particular treatment is known as the semi-classical treatment. And using the so-called rotating wave approximation and in the rotating frame of reference, the Hamiltonian of this two-level system is of the whole system is described by this Hamiltonian, where delta is the detuning parameter, that is omega minus omega 0. Omega is the laser field frequency. Omega 0, as I told, is the resonance frequency of the atom, and capital omega is the so-called Rabi frequency. Then we can actually write it in this basis state as well. Here sigma, for example, represents the atomic lowering operator, and sigma dagger represents the atomic raising operator. Then we went on to calculate the probability of getting the system in the excited state, and then this is given by this general expression here. Omega tilde is the generalized Rabi frequency, and we see that when the resonance condition is there, that means delta is equal to 0, the atom can go from the ground state to the excited state fully when omega t is equal to pi. But that is not the case if this resonance condition is not there, if delta is not equal to 0. So these things we discussed. Then in lecture 5 we discussed the drastic picture of the two-level atom. The idea was that when the laser light is impinged on the two-level atomic system, the ground state and the excited state are no longer the eigenstate of the two-level system, and then still we can find out the eigenvalues and eigenstate of this Hamiltonian, dressed Hamiltonian, and we found it to be, it has two eigenvalues, E plus and E minus, and the dress states and the corresponding eigenstates are is represented by this plus gate and this minus gate here, and this angle theta is known as the Stackelberg angle, and this is associated with the Rabi frequency and the detuning parameter by this expression here. And we went on to discuss the so-called avoided crossing here as well. And in lecture 6 we learned the density matrix formalism in the context of two-level system. We saw that if we consider a single two-level system or a pure system which is simply represented by this wave function, then the density operator is written in this form, and in the basis ground state basis, ZE basis, basically the density operator can be written by this 2 by 2 matrix, and the expectation value of an operator A can be worked out just by taking the trace of the product of the density operator and the density operator. And we also learned about the properties of the density operator. For example, the density operator is Hermitian, trace of rho is equal to 1, and the eigenvalues of rho are real and non-negative. But rho does not obey Heisenberg equation, and this is basically due to the fact that though rho is Hermitian, it does not correspond to any physically measurable quantity. Then the mixed state, if we consider a mixed state, the density operator is given by this expression. And how to find out whether a system is mixed state or pure state, you just have to take the rho square of the density matrix and then take the trace. If the trace is rho square is found to be less than 1, then it corresponds to a mixed state. On the other hand, if trace rho square is equal to 1, then that corresponds to the so-called pure state. So here we are, if it is less than 1, then the density operator is basically representing a mixed state. And then we discuss the reduced density matrix. If we are interested say only in the system, not in the surrounding, then we can always trace out the system by taking the partial trace of the whole density matrix of the system plus the surrounding, and then we can now then focus only on the system only, just by writing the density operator for the system. Then in lecture 7 we refresh our knowledge on quantum harmonic oscillator. Basically we learn how the canonical quantization procedure here, and the idea is to first though the example was for classical harmonic oscillator, but this is valid for any classical system. The idea is to write down the Lagrangian. Here we are talking about classical harmonic oscillator. Lagrangian of the harmonic oscillator we just find out, then we find out the conjugate momentum of the system, and then we can write down the Hamiltonian of the system using this formula or expression, and then we can express the whole Hamiltonian of the classical system in terms of this coordinate and momentum q and p. And then the next step is to find out the canonically conjugate variable. To do that, we just have to find out those variables which satisfy the so-called Hamilton's canonical equation of motion. And if we find that out, then that will give us the canonically conjugate variable, and they satisfy the so-called Poisson bracket equation. And then quantization is straightforward. This canonically conjugate variable q and p are then replaced by the operators, corresponding operators, and this Poisson bracket is now replaced by this commutation relation, and then we can just write down the Hamiltonian of the system. So this is basically the way. And in the context of harmonic oscillator, we define the so-called annihilation and the creation operator, and the so-called the number state. And we also discussed couple harmonic oscillator, how to write down a two harmonic oscillator interacting with each other by some coupling coefficient, say kappa. Suppose this is harmonic oscillator, so this is what we have. So harmonic oscillator 1 and harmonic oscillator 2 having, say, spring constant, say k0 and mass m1 m2. And then we learn how to write down the Hamiltonian for this coupled harmonic oscillator system in the so-called rotating wave approximation. Then we went on to discuss how to quantize a traveling electromagnetic wave. The idea was to, again, here to find out the canonically conjugate variables. We started with this traveling wave electric field, and using the Maxwell equations, we worked out this equation where this E0 characterizes the state of the electric field in a given mode. We focus only one single mode, and the real part of the electric field E0 and imaginary part of E0 corresponds to the canonically conjugate variable within a multiplying factor, but we prefer to do in the normalized unit. So therefore we wrote E0t in this form, where alpha is a normalizable variable, a is a constant to be worked out, and this is straight away we get this equation from the Maxwell equations. And then defining the variables, and ultimately we did the calculation when we were able to get the Hamiltonian in the form of the well-known form of the so-called harmonic oscillator. And then we went on to find out that if we just write this alpha as a alpha in terms of q and p, if we defined it like this, and then we'll be able to write it as here we have written it, harmonic oscillator. So, and then to decide whether this q and p satisfy the are they really the canonically conjugate variable, then we found out this well-known equation using the Hamilton's canonical equation of motion that confirms that these q and p are canonically conjugate variables. Then quantization is straightforward, and thereby we were able to show that this electromagnetic wave, a traveling electromagnetic wave, the mode of a traveling electromagnetic wave behaves like a harmonic oscillator, quantized harmonic oscillator, and the electric field operator also we can write in terms of this annihilation and creation operator. Then in lecture 9 we went on to discuss the quantize the standing electromagnetic wave, and there the procedure was analogous but with some difference, because now we have to satisfy some boundary condition, because if it is a standing wave, the electric field is 0 at the boundaries at, say, z is equal to 0 and at z is equal to L. So these boundary conditions has to be satisfied. So thereby immediately we find that this wave vector is discretized, and because the boundary conditions has to be satisfied, the vector potential and the electric field has to be taken in this form, and the magnetic field is taken like this. And we worked in the so-called Coulomb case. So divergence of A is equal to 0, the background electrostatic potential was taken to be equal to 0, and then electric field is simply we can express it in terms of the vector potential. Then we using the Maxwell equation, we arrived at this equation, and then defining a normalized variable alpha of t in terms of the vector potential and the electric field. Then we got this equation from Maxwell equations, and then we write down the Hamiltonian like this, and ultimately we were able to show that this again, even a standing electromagnetic wave behaves like a harmonic oscillator, and the quantization was straightforward. Again, we got the canonically conjugate variables as our q and p. In physical unit, they are basically the vector potential and the electric field. With multiplying by appropriate factor, they behave like canonically conjugate variables. And then we were able to finally show that this also this standing electromagnetic wave, when quantized, it behaves like a harmonic oscillator. Now we can express the vector potential, and these are physically measurable quantity, electric field, in the operator form. And after that, we discussed the so-called coherent states. It is one of the important quantum states of harmonic oscillator or electromagnetic radiation, because we now know that quantized electromagnetic radiation behave like harmonic oscillator. We saw that this coherent state is nothing but displaced ground state, and d alpha is the displacement operator, and this coherent state can be expressed in terms of the number state as well in the in by this popular expression, and this coherent state is normalized. Then we found out that this average number of quanta in the coherent state is basically mod alpha square, and it satisfies the so-called Poisson statistics or Poisson distribution. And we found that the variance in the number of quanta or number of photon is equal to average in the number of photon. And of course, this is basically one of the characteristics of Poisson distribution. Then today in this class, we discussed about squeeze states of quantized harmonic oscillator or electromagnetic radiation. Now, as we are equipped with required fundamentals of quantum optics, we are ready to go to the next stage. In module 2 of this course, we are going to encounter our first artificial quantum system in the form of a Cooper pair box, which is the building block of circuit quantum electrodynamics that we are going to discuss in our course. I will first give an overview of circuit quantum electrodynamics. Then I will build up the fundamentals of circuit QED from the first principles. So see you in the next class. Thank you.